Well, thank you very much for the very warm introduction. So today I would like to share how recent improvements on our automated patch clamp system have enabled new recording capabilities, like using the high resistance HiR QPlate, HiR QPlate and low noise new Q amplifiers. So here's today's outline. So I would like to start with a high resistance plate enables the lysosomal patch clamp and also small cell red blood cells patch clamp. And then we switch to the amplifier. With amplifier, it is unable to the single channel recordings and also transporter recordings. Yeah, it's all the developing assay, so it is may not matured, but I would like to show the new capability on our systems. So high R plates. This is with the smaller patch hole size and resulting in the patch resistance is usually normal one is around 1.8 mega ohms. But this high resistance plates depending on the solution, but it can range in the 3 to 7 mega ohms, so much smaller size, patch hole size. And we developed the new amplifiers, so with low noise and higher sensitivities. Together with combination with these new technologies, we are able to record from the cell organelles or small cells like red blood cells. And also we expect more stable recordings from the neurons on the immune cells. But today, I would like to show the data from the organelles, especially the lysosomes. Yeah, so the important concept is matching whole size to the biology. So especially, sorry. So for the rhizome is very small and extremely small, and usually in our original plate cannot capture or even hold the clamps, the whole cell protocol. So it is unable to record from such a very small target or very difficult. So for example, this is a normal chip. The whole size is larger than the new one. So the lysosomes can be a little bit increase the resistance. That's suggesting the membrane comes to the hole and almost catches, but drops. So it means that it's released or even maybe the pass through the hole. But now we have the smaller hole size. It can stably hold the membrane of the lysosome and go through the whole cell patch clamp configurations. So for this lysosomal assay, the first target of the ion channel is TRPML1. So this is a non-selective cation channel. So as Dr. Chen explained, this is a very important ion channel. So included in the lysosomal exocytosis, trafficking, and autophagy ion homeostasis in the lysosomes. And also this dysfunction of this ion channel causes the lysosomal disease and neurodegeneration and metabolic disorders. But Dr. Chen shows more disorders related to the malfunction of this channel. So this is a very important therapeutic target. So in this work, we have the collaboration with Dr. Bastien Masson from the Ori Bioscience. This company develops the purified lysosomes ready to the assay. So they provide the sample of the lysosomes expressing the triple ML1 overexpression. So our research scientists, Eliska, work together, and we using the Cube 384 high throughput machine, we successfully established the lysosomal recording at around 75%. That means about 219 lysosome recordings using the one single plate, so one time. So and also we confirmed the pharmacological response with the MLSA5, the activator of this channel, so increased the current. So, but it is not all the lysosomes. About 50% of the lysosomes confirmed this expressing this current, responding to the MLSA5. So we also tested the assay specificity by using the triple ML1 knockout lysosomes. So as a negative controls. As expected, we didn't see any response to the MLSA5. So we now confirmed that this current is originated by the triple ML1, and this is only shown only seen when this ion channel is expressed in the lysosomes. Sorry. So we further evaluated using the activator with dose response concentration dependence. So measured EC50 was 0.19 micromolar. This is a good agreement with published EC50 0.285 micromolar. So we further validate the assay and confirms the quality of the recordings. So finally, we also tested in the near physiological temperature assay. So the previous data was recorded at the room temperature, around 75% of the capture and the success rate. But at 35 degrees Celsius, we still have the 71%. This is very compatible. So this shows the assay is compatible with even the more physiological conditions, like temperature. Yeah. So next, sorry, it skips automatically. Next target is TMM175. This is also the lysosomal ion channel, the potassium channel, and also has the proton conductance. So it is involved in the pH regulation in the lysosome and the membrane potential, and also some other the homeostasis related channels. So dysfunction of this channel cause like the lysosomal, the impaired lysosomal degradation, and also increased Parkinson's disease risk is known. So this is also another very important therapeutic target. So first we recorded the TMM 175 currents by activating the DCP-IB. So in about 43% of the lysosomes, this means the 165 in one plate, the lysosomes were recorded and responded to this compound. So, and also blocked by 4AP. So this might be the nasty, but it blocks many kind of the ion channels. So this is confirmed as at least some ion channels. We expect that this is the one TMM175 related currents. So we additionally tested with the existence of the DCP-IB in the extracellular solution and also the change the potassium concentrations. So this potassium gradient response is from the 0 millimolar to the highest, the 120 millimolar calcium, potassium, sorry. And so, sorry. So in this, the independent two experiments shows a very similar EC50 values of the potassium concentration, like 50 millimolar or 47 millimolar. So it is very consistent. So together with pharmacological data, we confirm the reliable functional characterization of TMM175 using the using the automated patch clamp system. So yeah. Okay. So next topic is red blood cells. So this is a very small, in diameter 7 to 8 micromolar, micrometer, but the thickness is only 2.5, around 2.5 micrometer. So these red blood cells are among the smallest and the most flexible cells in the body. So because they lack the synthesis in the nucleus, locking the nucleus, and also the gradually lose the ion channels expressed on the membrane. So depending on the age, it can varies about amount of the expression level of the ion channels. So this heterogeneous channel expression is very challenging for the manual patch clamp. So this might be helpful with the high throughput automated patch clamp in this such a variable expression level target. So the channels here, the target channel here is the Gardos channel, so or KCA 3.1. So this calcium activated potassium channel regulates the red blood cell cell volume and the dehydration. So together with PS1. So this excessive activation of this ion channel could cause the blood disease like the sickle cell anemia or other blood-related diseases. So this is also the very important pharmacological target. So recording from the red blood cells requires both the size of the cells is also small, but the current of the Gardos is also small. So in the histogram, as small as 4 picoamps of the currents were recorded. So also because of the small cell size, it is very small or low capacitance in membrane capacitance as in the peak of the 2.5 picofarad. So it's very small size. So improved capacitance estimation and reduced noise using the low noise amplifier, we are able to record these Gardos currents. So here we show the representative Gardos recordings from primary red blood cells. This work is carried out under the collaboration with Dr. Kian Hasseri from the University of Copenhagen and together with our research scientist, Dr. Kim Botan. So now the channel activity was activated by the NS309, the activator of the KCA 3.1. And then it is also suppressed by TRAM34. So this confirms this current is correspond to the KCA 3.1. So yeah. So to summarize the first section of this high resistance, HiR QPlate assays. So we are able to record the TRPML1 and the TMM175 from the lysosome, and also from the red blood cells, we recorded KCA 3.1 channel recordings. So, yeah, together with the high resistance plate and the high sensitive low noise amplifiers, it's enabling the faster and reproducible research of lysosomal and other small cell ion channels using the automated patch clamp system. So now we move on the next topic, the single channel current recordings. This is this study is small current targets. It requires more than the hardware hardware development, but also the optimize optimize hole size, consumables, low noise amplifiers, and also the assay design, and also the software development using for the data analysis. So combined with the collaborative work of these mechanical and biological assay development, we are now able to do the single channel current recordings and also transporters and more small currents upcoming. Today I will show the data about these two recordings. So before start showing the data, it is also very important to do this work is the built-in analysis. Development of the built-in analysis is also very important. Using our software, data analysis software, this can detect the currents, single channel currents, traces, and also make the current histogram automatically, then calculate this IV, and also calculate the conductance automatically. So this enables the experiment more efficiency. So here is the example of using the BK channel, big potassium channel. So this is relatively large current with even with a single channel. So in this part, we can see the discrete opening and closing events are observed by the single BK channels. So now we applied the beta essence, which creates the ion permeable pore on the membrane. So it enables to replace the solution in intracellular solution with the extracellular solution. So together with the essence, we applied the low potassium extracellular solution, and this replaces the or changes the concentration, intracellular potassium concentration. So now, in this case, we see about plus 80 millivolt of the reversal potential or equilibrium potential. So that is very close to with the pipette solution potassium 120 millimole and 4 millimole. So it corresponds by calculating using the Nernst equation. It might be like 84 millivolt of the reversal potential. So it is very close to this reversal potential. Then we switched the extracellular solution to the 120 millimolar potassium concentration. So this shifts this IV plot towards the zero, but it does not come to the completely zero, but still in this direction. So it shows that it suggests that this maybe this intracellular potassium may not reach to the 120, but it's a little bit higher than, at least more than the 4 millimolar. So this confirms the single channel recording, and the pursued inside-out recording configuration is possible. So also we tried the giant unilaminar vesicles. So the aromatine is applied, and we recorded some currents. So maybe it is also possible to utilize the GUV for the single channel recording study. So finally, we go to the transporter assay. So the target is the natrium calcium exchanger to NCX2. So this recording is very based, rely on the controlled experiment condition, like block all background currents and maintain osmolarity, stable temperature. So the recording condition should be the perfect. And then we tried the recording of we only get about half, 50% of the cells showed this current, but still we see the reversal and forward currents of this transporter. So, and also blocked by ORM 10103. So also we confirmed the nickel sensitive currents. When this transporter is expressed in the CHO cells using the inducible system. So with or without induction, so shows no current, or depending on the time of the induction, it shows the currents. Also, the dose response of the ORM 10103 and SEA 0400 both showed the dose response. So the second summary is we have evaluated the single channel recording using the PK channel, but maybe we are able to more recording from the other channels, and also we recorded the transporter currents. So yeah, the take-home message is that we are now able to patch clamp from the rhizome, organelle, red blood cells, and also possible to single channel and transporter current recordings. So I would like to thank to all my colleagues and collaborators together with working of these assay development. So we are always open to future collaborations for the development of new features. So thank you so much for your attention.